In this video, we're going to talk more about conditional probability, and this is also partially a setup for the next topic, which is Bayes' theorem. Okay, so let's start with an example. Suppose you're working in an office where the printer often breaks, and the repair person only services the printer on weekends, and only if somebody calls them. On Fridays, there's a 75% chance that the printer is still working. And if the printer was working on Friday, the probability that it will work on Monday as well is 95%. If the printer wasn't working on Friday, the probability that the printer will work on Monday is 83%. So suppose you were on vacation last week, you come in on Monday, what is the probability that the printer will be working? To get started, let's name our events just so that we're all using the same letters. Let's say F is event that the printer works on Friday, and M is the event that it works on Monday. So I'd like you to start by thinking about writing the statements in the form of a conditional probability, that is, in the form probability of B given A. So the two statements, if the printer was working on Friday, the probability that it will work on Monday is 95%. Can you write that as an equation using this term notation? And similarly, if the printer wasn't working on Friday, the probability that the printer will work on Monday is 83%. Also write that as an equation using that notation. After you do that, try to find the probability that we were looking for, the probability in general that the printer will work on Monday with no knowledge of last week. You might use a tree diagram to model this, although you don't necessarily need to. So I'd like you to pause and grab a piece of paper, try that out. We'll talk about it in a moment. Okay, let's start with a tree diagram and just think about what are the possible things that can occur. So either the printer was working on Friday or it wasn't. We'll write that as F complement. And either the printer was working on Monday or it wasn't. We'll write that as M complement, and similarly M complement. And the branches of the tree diagram that we're interested in are these ones. So we're interested in all the ones in which it was working on Monday, right? So we're interested in this probability as well as this probability. We want to find that total value. So what is that equal to? So this is, remember, this is basically multiplication right here. So this is the probability that it works on Monday. Well, how could that happen? That could either happen because it worked on Friday and then it worked on Monday too, or it wasn't working on Friday, somebody called the repair person, and it then worked on Monday. So either it worked on Friday and on Monday, or it didn't work on Friday, but it did work on Monday. Those are the two disjoint or mutually exclusive ways in which that event of working on Monday could occur. So what is that then equal to? That's equal to the probability that it worked on Friday times the probability that it works on Monday given that it worked on Friday. So this is just the multiplication rule. The probability that works on Friday and Monday is the probability that it worked on Friday times the probability that it works on Monday given that it worked on Friday, plus the probability that it worked on, the probability that it did not work on Friday times the probability that it works on Monday given that it did not work on Friday. And I'd also asked you to write these two statements in the form of probability of A given B. So the first one, if the printer was working on Friday, the probability that it will work on Monday is 95%. So in other words, we know the printer was working on Friday. The probability then that it works on Monday is 0.95 or 95%. The probability that knowing it worked on Friday, so this is always what we know, and the first part is what we're looking for the probability of. The probability that it works on Monday, knowing that it worked on Friday, is 95%. The probability that it works on Monday, knowing that it was not working on Friday, is 0.83 or 83%. So that's translating those two statements above into equations using the A given B notation. Okay, so now we can use that to plug in our probabilities. So the probability that it does work on a Friday, we said was 75%, so 0.75 times the probability that it works on Monday given it didn't on Friday. That it did on Friday, that's 95%, so 0.95 plus probability that it doesn't work. Well, using complements, the probability that it doesn't work on a Friday is 1 minus 0.75, so 0.25, and the probability that it works on Monday even though it wasn't working on Friday, that's our 0.83. And so we can throw those values into a calculator and we will get 0.92. So the probability that the printer works on Monday with no knowledge of what happened the week before is 92% or 0.92. So to think about this in a more general sense, if we've got two events A and B, so we have our event A and our event B, well, all the ways that A can occur, either A is happening and B is not happening, or A is happening and B is happening, and that constitute all of the different ways that A can occur. A happens and B happens or it doesn't. And so the probability of A, this probability, is equal to the probability that A occurs and B occurs plus the probability that A occurs and B does not occur. And then, so this is using the idea that these are mutually exclusive events. Then we can further simplify that or write it in a different way and say that I know by the multiplication rule that the probability of A occurring and B occurring is the probability of B times the probability of A given that B occurred plus now the probability of this, the probability that A occurs and B does not occur is the probability that B did not occur times the probability that A occurs knowing that B did not occur. So we're just using the multiplication rule twice. So basically that's the theorem we're using. We could also write that as probability of A equals probability of B times probability of A given B plus probability of B complement times probability of A given B complement. And even more generally, if B can occur in K different ways, so not just B or not B, but maybe we have events B1, B2, up through BK, then the probability that A occurs can be written as the probability that B1 occurs times the probability that A occurs given that B1 has occurred, plus the probability that B2 occurs times the probability that A occurs given that B2 has occurred. Yes, that's right. Plus the probability that BK occurs times the probability that A occurs given that BK has occurred. All right, let's use the same example to motivate another relationship between conditional probabilities. So sticking with that same example of this office, where on Fridays there's a 75% chance that the printer is working. If the printer works on Friday, the probability that it will work on Monday is 95%. If the printer wasn't working on Friday, the probability that the printer will work on Monday is 83%. So I'd like you to find what is the probability that the printer doesn't work on Monday, given that it was working on Friday. So this is a slightly easier problem, but try that out and we'll talk about it in a second. Okay, what is the probability that the printer doesn't work on Monday, given that it was working on Friday? One way we could think about this is that the sample space is being reduced. So instead of like all possible events, we're just working with the assumption that yes, the printer was working on Friday. And either the printer works on Monday or it doesn't. So now, in all cases, we are certain that the printer will be working on Friday. And so that means that the probability that the printer works on Monday, given that it was working on Friday, plus the probability that the printer wasn't working on Monday, given that it was working on Friday, is 1, because that's our entire sample space. We're just assuming the printer was working on Friday. And so the probability that it was working on Monday, given that it was working on Friday, plus the probability that it wasn't working on Monday, given that it was working on Friday, is the whole thing, is the total probability. And therefore, the probability that we're looking for, the probability that it wasn't working on Monday, given that it was working on Friday, is 1 minus the probability that we have above. If it was working on Friday, the probability that it will work on Monday is 95%. So 1 minus 0.95, and that's 0.05 or 5%. More generally, we've got this sum of conditionals probabilities rule, that if A1 through AK represent all the disjoint possible outcomes or variables for a process, so above it was just the printer works on Monday or it doesn't, just 2 possibilities, but there could be a situation where you have many more possible outcomes, different die rolls or whatever, then the probability of A1 given some variable B plus the probability of A2 given B plus ... plus the probability of AK given B is equal to 1. And as we have before, as we have above up here, just with different variable names or event names, the probability of A given B is equal to 1 minus the probability of A complement given B. All right, let's do one last example. Suppose that in a certain course, if you study for a quiz, the probability that you'll get a B or higher is 85%. If you don't study, the probability that you won't get a B or higher is 70%. You study for quizzes 90% of the time. What is the probability that you get a B or higher on the next quiz? And just so we're all using the same notation, let's let B equal B or higher, the event that you get a B or higher, and let's let S be the event that you study. So pause, try that out on some paper, and we'll talk about it in a moment. Okay, so we're looking for the probability that we get a B or higher, and we know that that's equal to the probability that we study and then get a B or higher, plus the probability that we don't study and then we get a B or higher. Don't study, S complement. And then that is equal to, using the multiplication rule, the probability that we study times the probability that we get a B or higher given that we did not study, plus the probability that we don't study times the probability that we get a B or higher given that we didn't study. So that's, again, just using the multiplication rule. So all these things you can memorize as formulas, or you can, basically use the really basic knowledge that we have, mutually disjoint events or mutually exclusive events and multiplication rule to find that formula. And so what is that equal to? So we know the probability of studying. In general, we study for quizzes 90% of the time, times the probability that we get a B or higher given that we studied, we said is 0.85, plus the probability that we didn't study. So if we study 90% of the time, we don't study 10% of the time, times the probability that we get a B or higher even though we didn't study. Well, that's actually not what is given here. What we have here is the probability that you won't get a B or higher if you don't study. So what we have up here is the probability that we don't get a B or higher given that we didn't study. By what we saw above, that's equal to 1 minus the probability that we do get a B or higher given that we didn't study, or, we can also subtract over and get the opposite. So in other words, the probability that we get a B or higher given that we did not study is equal to 1 minus the probability that we don't get a B or higher given that we did not study. So that's 1 minus 0.70, that's 0.3. So this is a 0.3 right here. and 0.3. And now we can just add those two quantities together, and when we do, we will get 0.795. So the probability of getting a B or higher on the next quiz, given these assumptions, is a 79.5% chance.